This is 8.8, improper integrals. Let's just take a look at what that means. So we have some definition up here. An integral can be called improper if one or any of the following combination. So let's look at the first one. We have infinite as our upper limit right here. And the way to do it is introduce another variable, t. So set that from 1 to t instead of 1 to infinite, and then take the limit after integration for t approaching infinity, right? And then we also have infinite for lower limit right here. Now, another one is when you have discontinuity, right? For example, in this case, we take the upper limit, which is 8, but 8 is actually discontinuous for the expression that's inside the integral. So in that case, we have to take, introduce another variable t, and then taking t approaching to a from the left-hand side. The left-hand side, because 8 is our upper limit. So if we're looking at 0 and 8, we're at exact point A, it's discontinuous, right? So maybe there's a line going like this, and then we're just looking at the limit approaching from the left-hand side. Right. Similarly, for the lower limit, if the lower limit is undefined for the function, we will introduce the variable and take it from the right-hand side. Right? So like this, 0 to 9, and then discontinuous here, right? So we're taking the limit from the right-hand side, which is 0 and then the plus sign. Right. Now, if there is a discontinuity in the middle, right? For example, in this case, from -2 to 3, we're going to hit 0 in some case, and 0 is actually undefined. So in that case, we will split the integral into two parts, right? So like this, -2 to 3. So let's say it goes like this, and then at 0, there is a discontinuity right here. So we will take this interval, -2 to 0 from the left-hand side, and then another one would be from 0 approaching from the right-hand side to 3. So splitting up into two separate improper integrals. And let's see how that works out. All right, next let's look at some a quick review on limit as x approaches infinity. Right, so if we have 1 over x to the r power, where if r is positive, then the limit is going to go to 0. And if you have a rational function and the degree of the numerator is the same as degree of denominator, then it's just the quotient of the coefficient of the leading term. And if the degree numerator is less than the degree denominator, then it's 0. And if degree of numerator is greater than degree of denominator, which is it's going to be infinite, right? So this is pretty much the same as when we're comparing two functions, right? Which one grows faster and which one grows slower, and that determines the limit as x approaches positive or negative infinity. All right, so let's look at our first example when we have infinite upper limit. Right, so we're looking at the integral of 1 to infinity of e to -2x dx. Now, this is a graph showing that what we're looking at, right? We're looking at the area under the curve from 1 to infinity, right? So the idea is we have to rewrite it using limit first, right? So let's rewrite that. So limit as t approaches infinity. And then now, instead of 1 to infinity, we're going to do 1 to t. And then e to the -2x dx. All right, and then we can just integrate this. All right, so keep the limit. And then I integrate that, that would be e to the -2x over -2, evaluating from 1 to t, which gives us a limit of e to the -2t over negative 2 minus e to the negative 2 over negative 2, like this. Right? Let's clean this up a little bit. Right? So we have limit as t approaches infinity, 1 minus e to the negative 2. Oops. No, that's not right. All right, so that's going to be e to the negative 2t minus e to the negative 2 over negative 2. All right, and let's see, we can do, if you take t approaches infinity, that means this term right here will go to 0, right? Because that's 1 over infinity, so that goes to 0. So we are left with e to the negative 2 over negative 2, which is e to the negative 2 over 2, or 1 over 2 e to the e squared. Okay, and there we have it. Right? That's after the limit, so that whole thing is your final answer. And this is because the going to 0 is because limit of, as t approaches infinity, of 1 over e to the 2t is 0. Okay. All right. So the idea is you want to rewrite the infinite bounds, right? Either it's the upper or the lower one, with another variable, and take that variable to either positive infinity or negative infinity. All right. So here we have another one. So this one is a little different because when we look at the graph, the area under the curve, it seems like it's going to go on, it's never going to drop down to 0 like what we had in the previous example, right? So let's see what happens when we try to integrate this, right? Same thing, rewrite that as a limit from 1 to t, and e to the x, 1 plus e to the x dx. All right, and then go ahead and evaluate the limit, evaluate the integral. That's going to be ln of 1 plus e to the x. Right? If you're a little unsure on how to integrate this, just do u sub. Let u be 1 plus e to the x, and du is e to the x dx. Okay, and then you start from there, you'll get this integral. All right, evaluating this from 1 to t. And then we have limit of ln 1 plus e to the t minus ln of 1 plus e. Okay, and then we know this is going to infinity, right? To e to the infinite power, and then ln of that is still going to infinity. Okay, so in this case, we say that this integral is divergent. Okay, so if it goes to positive infinity or negative infinity, we say that it is divergent. And we'll take a look at some other example. All right, next let's look at one example with infinite lower limit. Right, so it's the same thing, but instead of positive infinity, we are working with negative infinity with a lower bound. So limit as t approaches negative infinity, and the integral going from t to 1, x e to the x dx. Okay, and we have a polynomial multiplied with an exponential. So here we're actually doing integration by parts. So I'm gonna do a tabular method, right? So taking derivatives and integrals, we have x and e to the x, right? Taking derivative 1 and 0 and integrate this e to the x, e to the x, right? And then all we need to do is multiply them. Right, so that's going to be positive, that's going to be negative. All right, and we have limit t going to negative infinity, and our result of the integral would be x e to the x minus e to the x, and we are evaluating this from t to 1. Okay, All right, here we go. Limit. And let's see what we have here. We have 1, so e minus e, and then minus t e to the t minus e to the t, like that. Okay. So that's 0, right? So we have limit t approaching negative infinity. And I'm gonna put this minus in, so I have e to the t minus t e to the t. Okay. Now, if you just take it to negative infinity, you actually get right here you get infinity over infinity, which is not going to make sense. That's an indeterminate form actually. So somehow we have to do L'Hopital's rule. All right, so to do that, I'm going to factor out e to the t, like that. And then I'm going to push e to the t down to the denominator. All right, so 1 minus t over e to the negative t. All right, and then you can see down now we still have indeterminate form, so we can go ahead and apply L'Hopital's rule. L'Hopital's rule. So we get limit as t approaches negative infinity of -1 and then negative e to the negative t. Right. Now we can put that in here. So when we're approaching negative infinity, this is going to be e to the infinity, which will make this a really large number. That'll be 0. Okay. Now, if the limit exists meaning if it's not infinity or undefined or anything, if you get a number like that, we say this is convergent, opposite of divergent, which is what we saw earlier. Okay. All right, so you can see that in cases like this, we are implementing a lot of the techniques that we learned earlier. For example, here we're doing integration by parts, tabular method. Right? If you forgot a little bit about tabular method, definitely look into that because it's very useful. All right, and I also included the picture for this example here. So you can see that we have some area that's below the x-axis, which is going to be negative, and part of the area that's above. So they cancel out, and in fact, they are actually exactly the same. That's how we get the 0 for the integral. All right, next let's look at when we have infinite for both upper and lower limit. So basically we want to split them up into 2 separate integrals and maybe pick a point C that's in the middle. Right? Usually 0 is a nice place to pick. And for each of the integrals, you're going to take limit the lower one to negative infinity for a, the lower bound, and then infinity for the upper bound in the second one. All right, so here's a picture to go with this example. All right, so well, since that's symmetric, we're just gonna pick 0 as our cutoff point to make it a little easier. And actually, since it's 0, we can just find out one side of the integral and then multiply that by 2, and that will give us the area on the curve. Right? But for the purpose of this example, I'm just going to split them up into 2 separate ones, and then see what we're working with here. Okay. All right. So first, I'm going to split them up from negative infinity to 0, x squared, 1 plus x to the 6, and then add from 0 to infinity of the same thing. All right, and then next, assigning a new variable to them to take the limit. Let's say a going to negative infinity, and the integral going from a to 0, like that. And the second one, I'm going to take the limit as b approaches infinity, and then integral from 0 to b. So 6 dx. All right. Next, we just need to integrate each one of them separately. So what I want to do here is I'm going to do u sub. Move down a little bit. Since they're both the same thing, right? I just need to work out one of them and then I can just fill in the rest for the other one. All right, I'm gonna let u be x cubed. That means du is 3x squared dx. All right, that means 1/3 du is x squared dx. Right, that takes care of the numerator and the dx. All right, so let's see what we have here. Let's just take a look at one of them. So integral of x squared over 1 plus x to the 6th dx after u sub will be 1/3 integral du and then 1/1 plus u squared, right? And 1 plus u squared, that is arctangent, right? X squared plus a squared, or in this case, u squared plus 1 squared, right? So here we have it. That is going to be 1/3 arctangent of u. Okay, and then u, it's really x cubed, right? So you just do 1/3 arctan x to the 3rd power. All right. So let's just replace this with both integrals here and then we'll worry about the bounds. All right, let's see. So limit as a approaches infinity. Sorry, negative infinity. And then the first one, 1/3 arctangent x cubed going from a to 0 and then plus limit as b approaches infinity. Same thing, 1/3 arctangent x cubed going from 0 to b. All right, let's see what we have. Okay, so arctangent of 0 is 0, right? So we don't have to worry about that. So first part, limit negative infinity. That will give us negative 1/3 arctangent of a cubed. Okay, plus limit as b approaches infinity. So b, that'll be 1/3 arctangent b cubed, and then again arctangent of 0 is 0, so we don't have to worry about that. All right, and let's see what we have here. Okay. All right, so evaluating limit at negative infinity. So negative infinity to the 3rd power would still be negative infinity. So when is arctangent negative infinity? So remember the arctangent goes from negative pi over 2 to pi over 2. Right, so let's do a little work here. So x goes from arctangent, my bad. So let me reset it. So negative pi over 2 arctangent and then pi over 2. All right, so negative infinity, you're actually approaching negative pi over 2. So this will be negative 1/3 negative pi over 2 plus 1/3. And now it's positive infinity, so arctangent is approaching positive infinity when the angle is pi over 2. Right? So pi over 2. Yeah. And let's clean this up a little bit. What is that? That's pi over 6 plus pi over 6. That'll be 2 pi over 6, which is pi over 3. All right, and this is convergent. Okay, cool. All right, so taking, if one of the bounds on the integral is limit, or even if both of them are limits, it's pretty straightforward, right? Just need to rewrite it with another variable and take that variable as a limit approaching either infinity or a negative infinity. And everything else is pretty straightforward. Next, let's look at discontinuity. So the first one we're looking at is discontinuity at the lower point. So at the lower point, it's 0, but as you can see on the graph, as we're approaching 0, it actually goes up to infinity. Okay, so this is the case where we have to take the limit to 0 from the right-hand side, right? So let's rewrite this as a limit. So limit as t approaching 0 from the right-hand side. Now we're taking the right-hand side because we're looking at 0 as the lower limit, right? And then perform the integration normally. That's x to the negative 1/2 dx. I integrate that. You get x 2x to the power of 1/2, right? And then 9 t to 9. So that gives us limit of 9 squared is 3, so 2 times 3 is 6, minus 2 times the square root of t. All right, so if we take the limit of 0 from the right-hand side, right, that's still going to 0, so that whole thing is 0, giving us the limit is 6, right? So there you go, that's it. All right, next we're looking at discontinuity at upper limit. Okay, so similar to our last one, but now the infinity is at 8, which is our upper limit. So we'll do the same thing, just with a little change. So now the discontinuity is at the upper bound. So we are actually approaching 8 from the left-hand side, right? So we have to do 8 with a negative sign like that. Okay, so limit as t approaching a from the left, integral of 0 to t, 8 minus x to the power of 1/3, negative 1/3 dx. All right, and let's evaluate the integral. Limit as t approaching to 8 from the left. That's going to be 8 minus x or 2/3 with a chain rule of a negative sign, and then the multiplied by the reciprocal of the power, which is 3/2. Like that, evaluating from 0 to t. Okay, so let's see that there's a negative 3/2, so we can bring that out. Limit t approaching negative 3/2, and then we can just evaluate a minus x to the power of 2/3 from 0 to t. Right, so that's 8 minus t to the power of 2/3 minus 8 to the power of 2/3, which is 4. All right, so let's see. Now, when we're taking 8 to the left-hand side, it's almost approaching 8, so that will be a 0. And then we're left with negative 4 on the outside, so that would be negative 3/2 times negative 4, which is positive 6. Okay? And that just happens to be the same number as the previous one. So you can see that they actually look alike, right, in terms of the graph. Right, but similar to when the bounce is limit, but the tricky part here is you have to be very careful. If it's the discontinuity at the lower limit, then we are approaching from the right, like that. But if the discontinuity is the upper limit, then we're approaching the left, like that. Okay, so be very careful of where you take the limit from. Okay, so the last type of discontinuity is when it happens inside the interval. Right, so let's look at this graph right here. Right, so they are both going to 0 as we're going away from 0, but at 0 it actually shoots up to infinity. Right, so but the integral we're taking actually goes from -2 to 3, which means in the middle here, this is where our infinite discontinuity happens. So in this case, we're going to cut the interval into 2 parts, separate them at 0, and then we're going to look at 0 from the left-hand side and from the right-hand side for those 2 intervals. Okay, so the first one, we're going to look at -2 to 0. And the second one is 0 to 3. Okay, so now we have two separate discontinuity at upper and lower limit, right? And then you just perform them the same way you would with if you were just working with one of them, right? So let's see. A going to 0 from the left hand side because this is the upper limit. So -2 to a, x to the -4 dx plus limit taking b to approaching 0 from the right hand side because the 0 now we're looking at is the lower limit. And then the integral from b to 3. All right, and we just evaluate each one of them separately. That should be pretty straightforward. So let's see. Limit a going to 0 from the left. That's going to be x to the power of -3 divided by -3. Going from a, -2 to a. And the second one is limit 0 from the right. And x to the power of -3 over -3. Going from b to 3. All right. So just working it out. That's -1 over 3 a cubed minus negative, that's a negative a, positive 24, so 1 over 24 plus limit b going to 0 from the right, and 3, that's 27, 81, -1 over 81 minus, and with the minus here, so that's a plus, 1 over 3b cubed. Okay, and let's see what we have here. Just need to evaluate the limit. Okay, so let's look at the first one. It's going to 0 from the right, left hand side, so negative. So negative with the negative, that's going to be a negative number that's very close to 0. Right, so this is going to be a negative number that's very close to 0. With the negative, it's going to be positive, right? So that's, this whole thing goes to positive infinity, right? If you want, you can just take like -0.00001 and type that into the calculator. You can check. All right, and here going to 0 from the right hand side, so everything is positive, right? 1 over a very small positive number, right? That's going to be going to infinity as well, right? So both of them are going to infinity, right? So we can say that this is divergent. Okay, and that's it for this example. All right, this next one, we're looking at double improper. So we have a discontinuity at one end, and then on the upper end, we have infinity. All right, so the idea is we're going to split into two separate integrals, and then you can pick a constant c, any number between 0 and infinity. Right, so my suggestion is to take 1, right? That's a little easier. And then you will have two integrals. And then you just evaluate each one of them as an improper integral. So I'm going to leave this one to you to try on your own, and we will talk about this one when we meet for weekly group work. So the answer for this improper integral is 1. Okay, and let's see if you can get it. So we're looking at our first comparison test. So this one is called a direct comparison test. So basically what we're doing here is we're comparing the areas under two different functions, right? So we have the graph here. Now, actually, let me make it a little bigger. All right, so let's just focus on point A. Now, if integral of f of x is convergent, then integral of g of x is convergent. So what we're looking at here is the area under the curve f and area under the curve g, and with the same bound. So let's say if we can show that the area under the curve f is finite. So if area under f is finite, meaning that it's some number, a constant that we can represent the area under f, then the area under g is also finite, right? Because we know that f is greater than g, so the area under f will be greater than the area under g. But if we can show that the larger area is finite, then the smaller area will also have to be finite. On the other hand, if we look at part B, where we're looking at divergent, now divergent goes the other way, right? If we show that the small curve, the area under G is infinite, then the area under F is also infinite. Right. So A and B, they're actually opposite of each other. If we show that the smaller area, namely G, is infinite, then the area under F is greater than the area under G. But G is infinite already, so F is greater means F has to be infinite as well. So that's the basic idea of direct comparison test. And let's look at a few examples. Okay, so our first example, we're taking a look at the area under the curve of x over x cubed plus 1 going from 1 to infinity. Now, when we are approaching infinity, this 1 is not going to affect that much. So we can actually drop this 1. So basically what we're looking at is we have x cubed plus 1. And this is actually smaller than or equal to x over x cubed, right? Without the 1. Right? The greater the denominator, the smaller the value is. Right? So that is can be simplified into 1 over x squared for x greater than or equal to 1. Okay, so since this is the larger one, 1 over x squared is the larger function than x over x cubed plus 1. If we can show that it's convergent, then the smaller one will also be convergent. Okay, so let's do that. All right, integral, and then take the limit as t approaches infinity, like this. And then that'll be limit of, oh shoot, it's not infinity. Should be t. Right, so that'll be x to the power of -1 and then a negative sign. Going from 1 to t. Okay, and then take the limit, approaching infinity. What do we have here? -1 over b plus 1. Right, minus -1. Yep. All right, and this is as that goes to infinity. Oh, not b. Sorry. T plus 1. Okay, and that goes to 0, means the limit is 1, which is convergent. Okay, and then we show that the larger area the larger one is convergent. So let me write it down what we're doing here. So we show that 1 over x squared dx is greater than or equal to the integral of x over x cubed plus 1, right? And this is also convergent. Okay, so we can say by direct comparison test, the integral going from 1 to infinity, x over x cubed plus 1 dx is convergent. Now notice that we're not worrying about exactly what this value is, what the integral is. All we care about that it is convergent, right? And so the same idea, this is our first case where we show that the greater function has a finite area under the curve. So the smaller function would also have finite area under the curve. And therefore, we say that it is convergent. Okay. Now let's look at another one. All right, so here we have another integral. So again, it's very annoying trying to integrate this, right? So the idea is, as we're going to infinity, e to the x is going to be a very small number, right? So e to the x gets small as x approaches infinity. So we can drop it. So we can drop e to the negative x. Okay. All right, so let's write it out. 2 plus e to the negative x over x is going to be greater than or equal to 2 over x, right? So we're eliminating the term e to the negative x right here. Okay. So we have a smaller function. So for a smaller function, if we can show that it diverges, then we can show that the bigger function also diverges as well. Right, so let's see, 1 to infinity and 2 over x dx. And you can see that this integral is very easy to work with, which is limit t approaching infinity, 1 to t, 2 over x dx. That is limit as t approach infinity to ln of x. Right, and then going from 1 to t. That is the limit of 2 ln t minus 2 ln 1, which is 0. All right, and then it's easily evaluated that this thing is going to go to infinity, which means it's going to it's divergent. All right. So here we are in the second case, right? So our original function, 2 plus e to the negative x over x, is larger than the function 2 over x, or larger than the function that has infinite area under the curve. So the larger function will also have infinite area under the curve, right? So we can say that by direct comparison test, the integral 1 to infinity of 2 plus e to the x, negative x, over x is divergent. Okay, and in this case, since it's divergent, we know that it goes to infinity. All right, so what if we pick the inequality in the wrong direction, right? So we have this example right here, right? So we omit the 3x, making it a larger function, but we show that the larger function actually diverges. So if the larger function diverges, then we cannot say the same about the smaller function, right? If the larger function converges, then we can say that the smaller function converges as well. So in cases like this, the direct comparison test is not going to work. And we will have to use some other test, which we will talk about right now. All right, so the other comparison test is called the limit comparison test. So what we're doing is we take two functions growing at the same rate, right? When we take the limit of the quotient of those two functions, you get constant. When we were doing comparing two functions, this means f and g grow at the same rate. Then we can say that these two functions, they actually behave alike. They either converge together or they diverge together, right? So this is a little different than a direct comparison test. So let's take a look at some examples. Okay, so we have integral from 2 to infinity of the function x over square root of x to the fourth plus 3x. Now, if we look at the denominator as we approach infinity, x to the fourth power is going to grow much faster than the 3x. So we can actually drop the 3x here. Right? So let me write it out. X to the fourth plus 3x. That is going to be less than or equal to x over the square root of x to the fourth, which is 1 over x. Right? Now we can drop the 3x, right? Because when x is large, this 3x is not going to affect the x to the fourth that much. Okay? Now we have shown that we have taken a bigger function, but we know that the integral going from 2 to infinity of 1 over x dx diverges. So in this case, direct comparison test is not working, right? Because we have shown that the larger function diverges. From direct comparison test, we cannot say the smaller function diverges as well. So in this case, let's try limit comparison test. All right. So next, let's just put them in the form of a quotient and then take the limit. And if we get the same thing, that means they behave the same way. Okay, so let's see. So limit as x approaches infinity of the original function, x over radical x to the fourth plus 3x over the larger function, which is 1 over x. All right, and let's clean this up a little bit. We get limit as x approaches infinity of x squared over radical x to the fourth plus 3x. Okay. So it's going to be infinity over infinity, but of course you can do L'Hopital's rule, but it's going to be very ugly, right? But we're going to use a technique from Calc 1, which is multiply the numerator and denominator by the reciprocal of the highest power. So multiply by 1 over x squared over 1 over x squared, like that. Okay, and the numerator, I have 1. And the denominator, if I multiply 1 over x squared into the square root, I get 1 over 1 over x to the fourth power, right? So in the numerator, it will look like 1 plus 3 over x cubed. Right? And then after you take the limit, right, the only term with the x is right here, that will go to 0. And then you're left with 1, right? So what we have shown here, if it's 1, we have successfully shown that 1 over x and x over square root of x to the fourth plus 3x behave the same. Behave the same way. And since integral of 1 over x dx diverges, then we can say that by the limit comparison test, the integral going from 2 to infinity of x over square root of x to the fourth plus 3x diverges as well. Okay, so this is a little bit different than direct comparison test. For direct comparison test, if this were the other way around, the inequality were the other way around, then we can say that, okay, it diverges, because if the smaller function diverges, then the larger function would diverge as well. But here we have the larger function diverging. It does not mean that the smaller function diverges as well. So we have to use the limit comparison test. comparing these two functions, and we have shown that they actually behave the same way. Therefore, we can say that if one of them diverge, then the other diverges. And we get that they behave the same way by taking the limit of the quotient of those two functions, and then we show that it's equal to 1, which is a constant. Therefore, they grow at the same rate, and they will behave in the same way as well. All right, and that'll be all for this section. It's quite a long section, so take your time and please visit me in my office hour if you have any question. Else, I'll see you next time.